Mr. Abbott here, and another session of boring activity explanations. We're looking at lab number 26, which you got the other day in class. Lab number 26 is called Carbon Dioxide and Global Warming. I'm not going to go through all of this. You were given two sets of data. One set of data at the bottom of the lab showed you carbon dioxide concentrations in parts per million. Okay, later on you had a second data table, and this data table was giving you data from 1958 to 1993, showing you the carbon dioxide level in ppm. ppm is a unit that stands for parts per million. So out of a million molecules of air, only 351 of them were carbon dioxide in 1993. Currently, today, in 2018, we're up to about 406 parts per million of CO2, so you can see that's a fairly rapid increase in a really short amount of time. Now, we watched a video showing that most of the data that you see is actually recorded on the top of a mountain in Hawaii. The mountain's called Mauna Loa, and they have been measuring the carbon dioxide concentration in Mauna Loa since 1958, 1959. This data table actually gives you all of the values, the average values for CO2 starting in 1959. If you put all of this data together, this chart happens to go up to 2014, you would produce a famous graph called the Keeling curve. Okay, it really displays how CO2 has been changing in our atmosphere. Now, the other graphs that I have here, one of the graphs you're going to draw should have a shape that looks something like this. All right, this is starting from 1960 and going through 2014. It's showing you the average amount of CO2, and obviously there's been an overall increase in the amount of CO2 that has been accumulating in our atmosphere. Okay, something is occurring that's adding carbon dioxide into our atmosphere. Now, if I flip this over, the second set of data that you're plotting should look something like this. Okay, if you look at CO2 levels not on a yearly average, but on a monthly average, what you're going to see with these CO2 values is you get a cyclic variation. So the CO2 levels increase sometimes and they decrease sometimes. Looking at this graph, you'll see up here, every single year, the monthly maximum is in May. Each year, you look at the bottom of this, and each year, the minimum is in September. So when you look at it, there appears to be an accumulation or a buildup of CO2 for part of the year. So from September to May, if we look at this, from September to May, you get a net gain, or we could use the term a surplus. We're adding CO2 to the atmosphere. From May back to September, instead of having increasing CO2 levels, during those months on a yearly basis, CO2 values are going down. All right. How do we account for the fact that sometimes CO2 goes up and sometimes CO2 goes down? Well, most of it's probably related to two processes. If you look at photosynthesis, okay, Sammy, what is photosynthesis going to do to your carbon dioxide concentration?
I don't know, Mr. Abbott.
Okay, can somebody please help Sammy? Miss Olson.
The more photosynthesis that occurs, the more carbon dioxide there is in the atmosphere.
Right, so CO2 removes right. CO2 is going to be used by photosynthesis. So when you look at photosynthesis, photosynthesis is going to remove CO2 from the atmosphere. And honestly, from May to September, that's when you get the most plant growth. We use less fossil fuels during that time frame. So overall, globally, CO2 levels tend to decrease. Now, if you look at fossil fuels, you should know that fossil fuels are things like coal, oil, and natural gas. But when you burn or use fossil fuels, the burning of fossil fuels for energy is going to be adding carbon dioxide to the atmosphere. And when you add CO2 to the air, okay, what we're concerned with is that gases like carbon dioxide, water vapor, and methane absorb infrared, and that makes the temperature of the planet go up. So the two general trends that you're getting on this graph is each year you gain more carbon dioxide than you lose. So there's a general increase. If I wanted to draw what the average for this sort of would look like, an average value would be somewhere in the middle, and the average CO2 would be going up. So on average, every year the values increase. That would be one trend, but there's a cyclic yearly variation related to the amount of photosynthesis and the amount of fossil fuels that are burned. All right, other things that you have to do with the lab. One thing it asks you to do is it asks you to calculate the rate of carbon dioxide increase from 1960 to 1990. Now, you should know that the rate of change is equal to the change in value divided by the time. Okay, 1990 to 1960 is 30 years. So we put 30 years into the denominator. All right, what was the CO2 concentration by 1990 according to the data that you have here? Does anybody have that number for 1990?
346.5 ppm.
All right, so that value should be 346.5 parts per million. Okay, when you look back at 1960, in the 60s, okay, we had been using fossil fuels, for a shorter period of time. Population was lower for a lot of different reasons. CO2 levels are less, but that should be 316.5 parts per million. All right, that's fairly easy. When I subtract those two numbers, that would be 30 ppm over 30 years. Okay, obviously I'm getting 1, but the unit should be parts per million per year. So we could look at that rate over time. Honestly, that rate is probably greater than 1 part per million per year now. All right, now at the top of this, you have to draw two graphs on the top. The first is a line graph. Okay, I'll go over the scales for the line graph. The second is a pie chart. Now, one thing you'll notice about the pie chart is all of these have to add up to 100%. If you were given a set of data like this and they didn't add up to 100%, you'd probably make a category for others. So we're going to look at and plot out that graph together. While I'm getting the data for that graph, this is how I would suggest setting up the other graph. Okay, make sure you put titles on your graph. So I would put carbon dioxide concentration at the top. Okay, on the bottom you had time in years. You have to cover the entire range. So I would go from 1950 to 2020. Okay, each line would be worth 2 years. Going vertically, all right, I would start at a minimum of 310 because our data starts at about 315, and I would go from 310 all the way up to 360. Okay, some of your points are going to be on the line. Like I started plotting the data, so the first point is on the line, the second point is exactly in the middle of the line, but I am not going to sit here and plot this. You know that CO2 values have been increasing, globally over the last 50, 60, 100, 200. It actually started from the beginning of the Industrial Revolution. Sammy.
If I went up by a different scale, is that okay?
That's absolutely appropriate. There's more than one scale. I picked this one because it would be easier. You could have gone up by 1.5s, but I chose to make it a little bit more obvious and a little easier, so I went up by the value of 2. All right, so let's take a look at the pie graph that you have to do on the top. When you look at the data table that you have for this, okay, your pie graph, I started setting it up already so we don't get really long videos, but your pie graph, it shows you in your data table that all of these different regions represent carbon dioxide sources. I relisted, because you should make a key on a pie graph. You should label your pie graph. But the 4 different sections that they had were power plants, represent 33%. So I'm starting at 33%. We're starting at 0, and we're going to read clockwise. So I put a little mark over here for 33%. Pie charts are really good for showing you percentages, so you definitely want to use a straight edge, but you go from the middle to there. If you don't have a highlighter, you could use a symbol or something like that, but you want to go from 0 to 33%. I like putting the words in there as well. So in here, I'm going to put power plants. If you like, you could put 33%. If you didn't, not a big deal because it's in your key. Cars and trucks are 22%. So 33 plus 22 goes to 55. I'm going to find 55 for the next segment. I'm going to go back to my center, and I'm going to draw carefully 55. And this I'll label cars and trucks. Okay, that's 22% of the total. Okay, you add 12 to that, you get to 67. 67 should be right there. So the smallest contributor, only 12%. You draw a graph like this. It says major transportation, 12%. Now, I'm thinking this means like railroads, planes, things like that. I don't know where this data came from, so I really can't tell you the exact value. Now, just to check my math, 67 plus 33 brings me back to 100. So this last segment, which is really significant, is if we look at factories and home heating. Factories and home heating represent 33% of the total CO2 based on this data. If you'd like, you can always take highlighters. All right, I might do like the power plants in yellow, and then I would highlight this entire wedge. Okay, so 1/3 of all of our CO2 emissions, I'm assuming this is for the US, would be from power plants. Maybe I'm out of highlighters, so I could choose like a slashy symbol, and I could make this section cars and trucks. I think I got another one. Maybe we'll go green for this one. Okay, so major transportation will be green. If you didn't color code yours and you use symbols, that's absolutely okay. Maybe I'll do the factories and the heating as vertical red lines. Doesn't really matter as long as somebody else is going to be able to read your key, but your pie graph should look something like that. All right, the bell's going to ring. Good luck with the rest of the lab. Take care.